Okay.
Hello, hi everyone. Welcome to the Geoscience and Geoenergy webinar of today, 20th of April 2023. This is our 113th webinar starting the pandemic. Today we have the pleasure and honor to host our dear colleague and friend, Dr. Remco Groenenberg, who is the scientific lead for subsurface energy storage of the Unit Energy and Materials Transition of TNO. TNO is the Netherlands Organization for Applied Scientific Research, is our national lab. And executive board member of EASE, might be reading EASE, which is the European Association for Storage of Energy. Remco holds a PhD degree in applied earth sciences, not so far from where Sebastian and I work, from Delft University of Technology. And also he holds his master degree, Master of Science in Geology from Utrecht University in Netherlands. His current activities include acquisition of contract R&D work, scientific oversight, and geoscience consultancy in the field of subsurface energy storage, energy system integration, and also reuse of energy industry assets and infrastructure to accelerate the energy transition. During his career, Remco has built up a long-term experience in applied geoenergy research. He held several positions in industry and academia working on R&D, demonstration, and commercialization in the fields of subsurface energy storage, geothermal energy production, CO2 storage, and oil and gas exploration and production. He currently leads the European-funded HyUSPRe, the topic of the talk today, project, which is a European-funded project, as I just mentioned, that assesses the feasibility of hydrogen storage in porous reservoirs. He's also a co-author of the recently published technology monitoring report on underground hydrogen storage, which is part of the IEA subtask 42 TCP Technology Corporate Program, which is also a kind of a collaborative and quite extensive work over more than a year, I guess, of work. And he did a lot of contribution on that report. And the report is, by the way, publicly available. We encourage you all to please go and download it and study that. It's a blend of all the sectors' inputs on it. And so Remco might also be able to even answer questions if you have any questions at the end as well. But here we have him for HyUSPRe project, and we are all very much looking forward to hearing his lecture. Thanks a lot, Remco, for graciously accepting our invitation. And to the audience, please note his lecture would last for about 30-35 minutes. And then afterwards, we will take the questions and hold the discussion session. Like always, please do post your questions in the text box and do not wait until the end of the talk to post your question. Please do text them any moment you feel appropriate, because your question will trigger other colleagues to also engage with him. And I'm sure Remco would like very much to hearing from you about your questions, comments, and also mutual interest. So without any further ado, Remco, we are all very much looking forward to hearing your talk. Thanks a lot once again.
Thank you, Hadi, for this very nice introduction, and also thank you and Sebastian for inviting me to present today in this wonderful Geoscience and Geoenergy webinar series. It's really an honor to do this, and on the HyUSPRe project, which is very nice also, of course, to be able to provide an update to the underground hydrogen storage community on where we are with our project. So let me, without further ado, move to the second slide. So maybe HyUSPRe for people, I had the acronym here. It's always a sport to find the right acronym for a European project. And in this case, we came up with HyUSPRe, Hydrogen Underground Storage in Porous Reservoirs. So I'm sure when you're familiar with and have experience with these kinds of European proposal writing phases, that this is one of the cherries in the cake to be able to come up with a nice acronym. But anyway, next slide is just an introduction to the HyUSPRe project. This is an R&D project granted by the Fuel Source and Hydrogen Joint Undertaking. in 2020. The call was in 2020, and the budget I've stated here is 3.5 million, of which 2.5 million is a subsidy from the European Union. The project duration is 27 months. It's originally, well, it ends in December 2023, but I think we're looking at an extension of 6 months. So it might even take until June 24 before we actually finish the project and present our final results. We have a consortium of 7 executive partners and 10 industry partners. I have a next slide on that, and TNO is coordinating the project. There is a Cordis website where you can find some details. I've linked that here, but of course there's also a HyUSPRe project website where you can find a lot more detail even. So the HyUSPRe consortium, we're very proud to have a great mix of industry, research institutes and universities here. Especially the support from industry is extremely appreciated in different forms. In-kind support with providing sample material, formation, water and rock samples and what you name it. Also data and expertise, of course, on their activities specifically and whatever relates to hydrogen storage. So very glad with that. Research institute, quite strong research institutes from the Netherlands, Austria, Italy, and Germany, and then 3 great universities from the UK, Germany, and the Netherlands. So a really nice mix of partners for this project. Yeah, maybe very briefly on the why of this project. Of course, I guess many of us know this already, and hydrogen is expected to become one of the clean and flexible energy carriers of future energy scenarios for electricity, industry, heating, and transport, certainly in Europe. But I see also in other parts of the world that hydrogen is gaining traction. Example, of course, is the US and Australia, Japan. And then, of course, the analogy for storage, of course, with natural gas is really apparent. It's already safely stored natural gas in large quantities in subsurface pore reservoirs in many countries in Europe. Including in depleted hydrocarbon reservoirs and aquifers to balance supply and demand on a daily basis and secure supply in cold winters. And yeah, if we are going to really use hydrogen at large scale, also to support the widespread integration of renewables like wind and solar, and making sure that we don't have to throw away a lot of electricity at times we don't need it, that we could very well use at times when the wind is not blowing and the sun is not shining. So basically the ability to time shift energy either in electrical form or by conversion to hydrogen and then use of the hydrogen as a carrier for other purposes. Then indeed storage is also going to be required as a flexibility measure. And then besides storage in salt caverns, storage in porous reservoirs could definitely be part of this future energy system, provided its technical feasibility is de-risked. And this is, of course, the key topic of this project, de-risking the technical feasibility, the techno-economic feasibility through targeted research, pilots, demonstrations, before underground hydrogen source can be implemented safely and economically. And also addressed here in our project is that we need a robust regulatory framework to some extent, viable business cases and best practices for responsible and societally accepted development. Right, so without societal acceptance, there basically is no project, and that is also clear. Okay, so maybe the areas and types of research in the HyUSPRe project. This is the diagram that basically displays the work packages and their relationships between each other. So we have 7 work packages. I would like to draw your attention to work packages 2 to 5, which are really experimental focused on aspects of geochemical reactions of hydrogen with rocks and fluids and reservoirs, microbiological activity, effects of those in reservoirs in the presence of hydrogen, flow behavior, diffusion, dispersion, and flow and relative permeability curves, for instance. And then on integrity and durability, basically investigating that for reservoirs, rocks, cap rocks, and well materials exposed to hydrogen. So basically, what are the specific aspects of hydrogen exposure? How does that influence the integrity and durability of wells, components, and reservoir and cap rock? Then there are other work packages more on assessment, modeling, and guidelines. So work package 1 here is about evaluating storage potential in porous reservoirs in Europe and mapping the location of these stores in relation to hydrogen production, demand side, and transport infrastructure. And that feeds then the experimental work, but also definitely the work in work package 6 and 7. 6 is more on actually taking the results from 1 through 5 and informing models that can be used for case studies onto how to operate these storages most optimally, and also in a safe manner, and providing guidelines for suitability assessment. How can you use these models, these case studies, to assess the suitability of reservoirs? And then 7 is the techno-economic assessment. So performing a techno-economic assessment of scenarios for hydrogen storage. So different scenarios for supply and demand of hydrogen in Europe, and then what role would storage play there, and developing a roadmap towards demonstration and implementation in Europe, which is the ultimate goal for this project. So I have to mention here that I'm definitely not the expert on all this. So I'm going to present in the next slides an overview of what we have realized and achieved so far with this project, which is just over halfway now, I would say. If you have specific questions that I cannot answer in the round of questions afterwards, then I'd be happy to relay your question to the experts that are working on this on the work package level. But I'll do my best to give at least an overview. So starting with work package 1, so addressing the question how much hydrogen could be produced and used in Europe. This is work by Forschung Centrum Jülich, Theresa Gross and Philip Dunkel. What they did is they looked at the literature up to, let's say, a year ago. In the meantime, of course, there's new literature, but that's always how things go. And they looked at demand projections for hydrogen in 2030 and 50, and also green hydrogen generation potential from renewables. And what they found here is that if you look at 2030, we could look at 400 to 750 terawatt hours of hydrogen demand in Europe, and in 2050, 3,000 to 5,000 hours, roughly. Comparing that to 2015 demand of 325 terawatt hours, this is, of course, an enormous increase. So not so much in 2030, but certainly in 2050, the expectation is that at least a tenfold increase would happen. And then if you sort of extrapolate that to potential storage requirements, assuming 30% storage, you're looking at 170 terawatt hours in 2030 and 1,200 terawatt hours equivalent in 2050. So those 1,200 terawatt hours in 2050 would be roughly what we do now for natural gas, a bit less, but still it's very significant, and that gives a bit of perspective to what demand figures can tell you about storage requirements in Europe for 2050. Looking at generation potential, then there's huge generation potential by electrolysis, of course, for hydrogen, electricity from wind and solar, and also terawatt hours on the left here on the bottom right graph. You see indeed differences between countries that are more that have more potential for wind generated hydrogen versus PV solar generated hydrogen, logically distributed between wind more potential in the northern countries versus more potential for solar in the south. But all in all, there is a lot of potential for hydrogen generation, purely from a technical point of view. That is, the economic perspective is not really taken into account here. If you look at the level of cost of hydrogen range, that could be achieved by production via these methods in different countries. You look at numbers between 1.65 and 4 roughly euro per kilogram. If you compare that against fossil hydrogen today, 1 to 1.5 euro per kilogram, that means that, and if you include CCS, then you have to add about 50 cents per kilogram. You see that there still needs to be a cost decline curve progression, right? So production of hydrogen by green hydrogen need to go through a cost decline curve. Technology need to also go to a technology learning curve. But the expectation is that we will be able to lower this significantly up to especially in certain areas, even fossil hydrogen numbers. Moving on to storage then, how much hydrogen could be stored in Europe? Also work package 1 with this time Edinburgh University, Andrew Kavanagh, Mark Wilkinson, and TNO, so Hamid Youssefi, my colleague, and myself. What we did here is we followed more not the conventional bottom-up approach to storage potential assessment, which you often see, for instance, in CCS. We followed a more targeted demand-led top-down approach, looking at starting from the existing reserve of underground gas storages for natural gas, which are expected to at least be partly reused for hydrogen. And what you see then is that between 320 and 450 terawatt hours of storage capacity for hydrogen could be realized in existing underground gas storages in porous reservoirs and aquifers. We call that the long list. And of course, the numbers depend. I mean, the range comes from different conversion factors applied. I'll come back to that in a bit. Of these 450 terawatt hours, there are 116 in depleted gas fields and 24 in aquifers. Plus, there is an existing underground gas storage reserve base in salt caverns of about 50 terawatt hours. If you look on the left here in the map, what you see is the circles indicating 10 storage clusters that we defined. And those storage clusters we took for further analysis for establishing a short list of representative sites. And these representative sites you can see as notional sites or template sites, providing a view on what a new additional site in the cluster could look like beyond the existing natural gas storage site, of course, for which we already know what they look like, at least from a perspective of depth and temperature and pressure ranges, etc. On the right, you see this table here, and on the bottom also a graph. The table is basically the exemplars and the prototypes that we defined. So for the different clusters, the exemplars are basically examples of existing underground gas storages for natural gas in the clusters, in 7 of the 10 clusters at least, that are representative of how they could be converted to hydrogen and what that would mean then for capacity. And also working gas to total gas, and for the prototypes is a similar story, but now looking at the entire underground gas storage portfolio in those clusters, and then sort of defining average representative additional storage sites that could conceivably be developed from gas fields in the region, in those regions, and what they could look like in terms of characteristics. So that's how we approach this. So exemplars and prototypes, and then in the bottom, what you see is how these prototypes, in particular, how they map against the ranges of capacity, working gas, total gas, working gas capacity over 90 days withdrawal, depth, Pmax, Pmin, temperature, field area, and permeability. The ranges that we find in the database for gas storages overall. So scenarios to meet hydrogen storage demand. So what could they look like then? That's what we did next. And this is all recorded, by the way, in the second phase report and the first phase report that we delivered for work package 1. It's available from the HyUSPRe website. But if you now if you take one scenario, try to match demand with storage, then for instance, this high demand, low supply scenario results in a gap of 1,000 terawatt hours. You need to have 1,200 terawatt hour storage demand. You need to meet that, and this assumes also a low percentage of conversion of existing underground gas storages to hydrogen of only 10 to 15%. The question then is where to find this additional capacity, and then in this case you would need 400 additional sites drawn from the clusters at cluster level from the shortlist, from the exemplars and the prototypes, or at least equivalent representative sites. And what you also see then is 70% of the capacity will have to be provided by 30% of the sites and 90% of the capacity by 50% of the sites. So at the bottom right displays this particular scenario, what it would mean for finding the capacity in the different region, Northwest, Central, Eastern and Southern Europe. And there are some non-cluster ones to arrive at 30 terawatt hours additional capacity for meeting the demand. On the left, you see in the map, there is, I would focus on the map. There you see the clusters displayed in green with their potential hydrogen capacity in this scenario. What you also see is a graphical representation of the backbone, hydrogen backbone, that the European Hydrogen Backbone Initiative is planning to develop, and how this connects the clusters. And you see in the background the different supply corridors for hydrogen into Europe. That is also from the Gas for Climate initiative, I believe. And here you also see the perspective of the import routes via Spain and through Africa, of course, via Spain, Italy, the east and the north, the North Sea, of course, and further north. So this is basically what is written down in the second phase report. A few words about the methodologies for capacity estimation that we proposed. So here we did a regional screening. And for that, you could use different conversion factor approaches to convert from natural gas storage capacity to hydrogen storage capacity for gas storages. And one we use, of course, is the common one, energy density based, which results in a conversion factor of 0.25. And then there is a rate limited 90 days withdrawal approach that we've also taken further and validated based on Amit et al. That's a 2016 publication from Amit et al. That is also in the report. And there we derived an empirical relationship. On the right, you see it, where we plot the conversion factor for a 90-day withdrawal, rate limited versus working gas to total gas ratio. And there you see that many of the sites in Europe, or the 40 sites that we took for this as representative and valuable and valid for this assessment, we took those and tried to find an empirical relationship. What you see on the bottom right here is that most of them cluster around the total mean of 0.33 for the conversion factor, whereas there are a few outliers on the top left that go more into the direction of 0.5. That's the subpopulation mean. And then the baseline of 0.25 is also shown. But indeed, you can also look at the empirical correlation, which is not bad, actually, which has a quite high correlation, and use that. I listed those here. So the heuristic versus the empirical. The heuristic is the conversion factor approach, whereas the empirical basically requires the working gas capacity for natural gas and the working gas to total gas ratio. And then you can calculate equivalent hydrogen storage capacity. It's in the reports. I guess I should move on. Any further questions I'm happy to take afterwards. There's an atlas we also developed, also on the website, on the HyUSPRe website, available there, where you can find some characteristics for each of these sites listed on the right. Work package 2 then. Impact of geochemical reactions with hydrogen. So this is experimental work done mostly by University of Edinburgh with minor contributions from TNO. In this case, Jan Terhege and Vincent Soestel. And of course, Edinburgh is Catriona Edelman, well known to many of you. And Ali Hassan Puyusband. And we also have some work here on TNO in Eindhoven, from TNO in Eindhoven in the next slide. But here what we do is experimental work on the determination of mineral rates, reaction rates with hydrogen, and it depends on pressure and temperature. These were conducted at Edinburgh on minerals, pure minerals like pyrite, calcite, dolomite, and gypsum, with a setup that is listed bottom left here shown. Quite interesting setup here, which allows for a lot of simultaneous batch experiments. And they observed essentially no reactions with all pure minerals up to 80 degrees in their setup. And the deliverable here is a database of mineral reaction rates with hydrogen. It's available on the HyUSPRe website. On the right here, there is another task, quantifying the potential pore space reduction and geomechanical changes in bulk rocks from hydrogen brine mineral interaction. Edinburgh did multi-cycle reactive flow experiments, conducted those hydrogen initiatives in recovery and rock image with X-ray computed micro-CT. Also there, they did not really observe any pore space reduction in the X-ray imaging experiments. They did observe changes in permeability related to pore size. The geomechanical impact specifically, so how does the exposure to hydrogen impact the geomechanical characteristics, is ongoing. This is work done by TNO by measuring geomechanical properties of the exposed rock samples. This is work in progress. So then a more in-depth study into the pyrite reactivity with hydrogen and what that would mean for the risk of hydrogen generation from the hydrogen-driven reduction of pyrite to pyrrhotite. Also leveraging earlier work or building on earlier work by Trusch et al., who established that reaction is sensitive to temperature, pressure, and pH, and also exposed surface area of the mineral pyrite. Trusch conducted these experiments at low partial pressures of hydrogen to maximum 30 bar, and the HyUSPRe experiments are performed at a pressure of up to 200 bars and a temperature of 150 degrees Celsius, exposing pure pyrite in brine to hydrogen. This is still underway, so we only have intermediate result here, but yeah, on the left you see the setup here, exposing pure pyrite submerged in brine to with a headspace of hydrogen atmosphere, sampling at regular intervals, measuring with GCMS, XRD, and/or magnetometer, the powder sampling post-mortem. And what we found so far is that we do indeed also see the reaction ongoing at 120 and 150 degrees and a pressure of 50 and 200 bar hydrogen. This is and also at the pH of 9, so that's a buffered pH buffered solution and an unbuffered solution. If you don't buffer, then the reaction lowers the pH of the formation water or of the brine and would basically self-terminate. But in this case, yeah, the measurement with the GCMS and also the XRD shows that this reaction is occurring. This is an XRD result here showing that by the triangles here that specific peaks in the XRD signal indicate that the pyrrhotite mineral is also present here in the post-mortem solid residue. So work in progress. I think we'll probably finish this work by end September and publish that on the website as well. Still quite a bit to do there. So work package 3, the Wageningen University is focusing on the impact of microbes on hydrogen storage in reservoirs. In this case, it's Diana Machado and Captain Anne Bart Lomans from Shell and Yehor Bereva. They're assessing the risk of loss of hydrogen through microbial metabolic processes, shown on the right here. Of course, potentially leading to generation of H2S in case of sulfate reducers through microbial sulfate reduction, and also loss of injectivity due to neo-wellbore plugging in bio-based solids from the growth of these microbes, excessive growth, I should say. Yeah, this basically builds on earlier work from Tyson et al. That established that temperature and salinity are the most constraining factors, and that the combination of temperature and salinity currently was shown to be a showstopper above 55 degrees and 1.7 molar sodium chloride. So there is a review of window of variability of the different microbial mechanisms relevant for subsurface hydrogen storage, published already as part of this project. Basically a literature review here already on the website. And currently ongoing are experiments leveraging samples from partners, from industry partners, performing incubations at relevant hydrogen pressures and temperature conditions, and then do the monitoring of the microbial community activity, methane, sodium, SO4 2 minus sulfate, and also biomass, of course. And then trying to establish the window of viability of the microorganisms and microbial enrichments, performing experiments with microbial enrichments in task 3.3. Experiments results so far, listed those here. Environment samples are exposed to hydrogen CO2 atmosphere at 1.7 bar. Also mixed environmental samples are exposed to pure hydrogen atmospheres of 1.7 bar. And also mixed inoculum incubations are used in the experiments with hydrogen exposure at 1.7 bar. And I think the most striking result so far is that there is the Wageningen finds that at 65 degrees with 2 molar sodium and 3 millimolars of SO4 sulfate. They find that sulfate reducers are active at 65 degrees which basically extends or redefines the known window of viability for these sulfate reducers to this combination of at least 65 degrees and 2 molar sodium chloride. This is really not my area of expertise. So if you want to know more about this, I would propose that you let me know, and I can contact the Burg, Diana. This was also presented during the webinar in February. Some of you may have followed that the webinar that HyUSPRe organized. So work package 4, hydrogen flow behavior reservoirs. This is from Clausthal University and Edinburgh. Birger Hageman and colleagues and Katjona Edelman and colleagues. They have reviewed the current state of art on hydrogen flow in porous media. The report is available. And they did experimental studies that characterize the hydrogen flow behavior in porous media. So trying to quantify or measure the effective molecular diffusion coefficient in different reservoir rocks for the hydrogen methane brine system. Also mechanical longitudinal dispersivities for the mix of hydrogen and methane brine, and determination of relative permeability curves for the hydrogen brine system. As mentioned, the report, the D44 and data sets are available on the HyUSPRe website. Of course, the relevance is that, the flow and mixing behavior of hydrogen in reservoirs and aquifers is extremely important in terms of understanding the level of the recovery that can be expected of hydrogen after injection on withdrawal, and also also I guess the need for purification or separation of the level of purification required to separate, for instance, methane from hydrogen, but also contaminants, of course. So the molecular diffusion coefficients, just very briefly. So what was found here, based on 29 measurements, is that where the influence of pressure, temperature, and water saturation was investigated. Effective gaseous diffusion coefficients were determined, varied between 5 to the -9 and 2.3 to the -7 square meter per second. And the results show clear trends, but deviations were observed at pressures above 75 bar and for the dependence on temperature at 100 bar. And the decreasing trend of effective diffusion coefficient with increasing water saturation fits the expectation. So it's clear that if you compare the effective diffusion coefficient for different samples at reference conditions, it's clear that it indicates that the effective diffusivity increases with porosity and permeability. And you see that also in the graphs on the right. This is for the Bentheimer sandstone reference sample here. Is shown the effective diffusion coefficient dependence on pressure, temperature, and water saturation to confirm here what we found on the left. Dispersion also results from 13 measurements on longitudinal and mechanical dispersion, investigating the effects of pressure, temperature, and flow velocity. Found that intermittent longitudinal mechanical dispersivity is varying between 0.018 and 0.06. And clearly that this dispersivity is not independent of these parameters. So fluid properties like density and viscosity definitely play a role in the dispersivity. Scheidegger's theory was found to sufficiently predict dispersive mixing between the two gases, hydrogen and methane, under subsurface conditions. But it was also found, based on the results, that the theory may not capture all the effects. So further investigation into this relationship between fluid properties and the dispersivities is definitely recommended because of the strong sensitivity to pressure in particular. Also in the report. And finally, the relative permeability curves work from Edinburgh. They experimentally determined the hydrogen brine relative permeability for a range of conditions and compare that with natural gas relative permeability curves for 2 sandstones and 1 carbonate rock. And of course they found that the relative permeability for hydrogen is influenced by pore structure and porosity. Increased porosity results in increased relative permeability. At higher hydrogen saturations, when pressure is increased, the viscosity of hydrogen increases as also, which reduces relative permeability. And salinity also has an effect on relative permeability, with an increase in salinity causing a reduction in relative permeability, possibly due to an increase in interfacial tension. In all cases, a strong water-wet behavior was observed for the different samples with respect to the relative permeability curves. So results from Edinburgh. Moving on to work package 5, durability and integrity of well and rock materials. This started a bit later and is still on the way. Not that many results yet. There is a review available that looked at analyzing and compiling and extending the relevant experimental data of well materials. This is deliverable 5.1. There's also a deliverable 5.2 on the effect of hydrogen exposure to cements. This is recently published in March. Other work planned to be done and ongoing focuses more on the exposure effects of hydrogen on reservoir and sealing rock formations and experiments on scaled down well systems with casing cement rock interfaces to evaluate the long-term integrity of these interfaces and in particular microannular formation on as a response to cyclic injection and withdrawal under hydrogen exposure. And Wageningen also has another task here to evaluate the effects of microbial influence corrosion at high partial pressures on wells in particular. So, and of course, what we hope to be able to say and recommend something about and conclude is the implications for hydrogen containment, reservoir injectivity, production, and quality of hydrogen, and recommend best practices for mitigation of loss of durability, integrity, and efficiency of the storage system. So briefly about the cement integrity tests that were done at TNO and recently finished is that so what we did here is cured glass sheet cement according to API standards, prepared according to API standards. Exposed this to hydrogen at 200 bars, these samples in Eindhoven, at TNO in Eindhoven. Did chemical analysis and also mechanical tests with reaction deformation, both unconfined compressive strength tests and cyclic loading tests. For instance, the cyclic loading, you see an example at the top right here, what we did. First cyclic loading test after initial loading, and then step loading to failure, and then afterwards unloading. And what you see is the stress evolution. And what we found is that, it's confirming earlier work reported, is that there is a limited effect of hydrogen compared to nitrogen. So no change of cement properties at our experimental conditions is basically the result. So this appears to not be the greatest concern, impact of hydrogen exposure on cements. Integrative multi-scale modeling, work package 6. This definitely started later together with work package 7. So this is just underway. What we want to do here is develop an integrated modeling approach for the overall performance, integrity, and durability assessment of the wearable and new wearable scale. That report is actually available on the HyUSPRe website. What is still ongoing is the improvement, extension, and validation of the open source simulator Dumux for flow and transport of processing porous reservoirs specifically for hydrogen. We want to also apply this reservoir simulator as well as other simulators like commercial ones, but also a new well-bore geomechanical model that TNO developed in 3 case studies, which we have in the meantime selected together with the industry partners. On the right, you see some of the characteristics of these industry studies. These case studies supported by industry, one for East, South, and Northwest region in Europe, and also a Central Europe case study for validation, model validation purposes, for which we also have measured data. And then ultimately, we hope to formulate a set of guidelines for the decision-making process and assessing reservoir site suitability. So almost final. This is the final slide. So Techno-Economics and roadmap for implementation. Also ongoing work started later, looking at investigating the role of hydrogen storage in reservoirs with your future hydrogen system using a spatio-temporal optimization model. This is more energy system modeling work. So moving a bit away from the subsurface towards the surface and more the integration to the energy system as a whole of these storages. evaluating equipment requirements and capital and operating costs for different hydrogen storage scenarios. This is deliverable 7.1, which will be published soon on the website. Estimating levelized cost of hydrogen and what share of that cost is taken up by storage, hydrogen storage, considering the supply chain from production to end user availability. Assessing environmental aspects, environmental risks and challenges in market design and regulations concerning underground hydrogen storage, and developing a roadmap for implementation. So this is still to come. This is a second phase project work. All the information on the HyUSPRe website. I really recommend to take a look for more detailed information on what I presented. Thank you for your attention. I'm happy to take any questions, of course.
Thank you very much, Remco, for this excellent presentation. You have been quite busy in the past year or so.
Yes. Thank you.
From capacity estimate to all the techno-economic assessments and all the feasibility and all the experiments is quite an active project. You did it also partly during the COVID as well?
Well, actually, we were fortunate to start just past COVID. That was a real blessing for us. But indeed, the European Union asks a lot for.
I know.
That's fine. That's fine. They keep us stretching on our toes.
Absolutely.
So
I understand what you mean very well. So thanks a lot. So there are plenty of questions posted, and you see also notice some friends and colleagues are also online. So I pass on to Sebastian to get the discussions ongoing.
Yes, thank you very much also from my side, Remco, for a really nice presentation, overview of this exciting project. So as Hardy said, lots and lots of questions. I'm going to start with a series of questions. They're all interconnected from Willemijn from TU Delft. And she says, hi, Remco, thank you for the very interesting presentation so far. If 30% of the reservoirs are good enough for about 70% of the total demand for storage, would it be a good idea to select the most suitable few sites, say 2 to 3, and make sure the technology can be deployed first before we move on to scale up to the remaining 70% capacity?
Yeah, thanks for that question. Of course, theoretically, that would be a great idea to start with the most suited site. But of course, there is always an economic perspective, and these sites are owned by operators, of course. So. Especially when talking about underground gas storages, they are still in use, right? So there, I would definitely think that there is the aspect of conversion of underground gas storage to hydrogen storage, and the timing of that conversion, which is of course important. So for pilots and demonstrations, I would definitely of course a more suitable site, yes, but in the end. Different actors are looking at different sites already and looking at their own site suitability, the most suitable site in their portfolio, and proposing projects or doing projects internally already. So I guess ideally you would do it that way, but the practicalities are making a big difference in the end.
Okay, so then thank you. Willemijn tries to pin you down a little bit now and says, if you were to pick the most suitable sites in the EU continent, which locations are most suitable in your view to host a few commercial UHS projects?
Yeah, well, no locations.
It's a small community that's not being recorded, so whatever you say is going to stay between us.
No, that's fine. I understand that. No, I would at least, and that's also what we advocate in the deliverables that we have on Work Package 1, is that at least do pilots and demonstrations in different regions in Europe, and those reservoirs then be representative of the portfolio of that region, right? So and it can be a depleted gas field, it can even be an aquifer. But at least make sure that there's a good spread between Northwest Europe, Central Europe, East Europe, and South Europe, because it's clear that there are different supply routes envisaged, and in the end, we will need storage in all these regions. So I guess on a regional level, look closely at what site is most suitable, and is also available, because availability is also quite essential, is available for an injection test or even a demonstration. So.
Sorry to squeeze some quick remark here. Arno is here also from HyUSPRe, and Jan Lagalo as well. So did you get any cooperation between the two projects to get their trapping analysis? Which sites did you study? You know, there are many, many reservoirs in the European continent.
Yeah, I guess if I can comment first, because we were 1 year trailing them. So I mean, a lot of their work was already done when we started, I think. So of course we looked with great interest at their results. In the end, we decided to follow a slightly different approach. Also, we felt it might be better to complement each other rather than do the same thing twice. Having in mind also that our big funder, European Union, is I mean they wouldn't want to spend the same money on exactly the same thing twice, right? So we took that into account actually. So that was our benefit. I don't know, maybe Arno or Jan, you can.
So they got from CCS type of trap analysis and tried to adjust it to your hydrogen. From my understanding, it looks like you just got the whole map of the reservoirs and tried to see which one would be this suitable one, right? Or did you get any CCS trapping analysis already as the
we
first?
Didn't.
Oh, okay.
No, we did not. No, we took the existing reserve in underground gas storages as a starting point, and assume that there are many gas fields in the same region of those sites, right? That could be potentially suitable. Of course, you would need to do a screening process, which would definitely be done when those sites would be in scope. So that's how we took it basically.
Very exciting. We see different angles to the same problem. This brings a lot of perspective, so to make it more confident, the whole.
Yeah, exactly. Also because what we basically, how should I say that, postulate is that, I mean, there is an emerging backbone already, right? And gas storage are already connected to that backbone. So it would make sense that hydrogen storage will emerge along those backbone routes too, right? So yeah.
Sebastian, mute me, please.
No worries. You mentioned Jan, and Jan asked a question and says, hi Remco, do you consider carbonate reservoirs for geochemical reaction rates? And I may add, I'm going to do it in Hardy now, carbonates perhaps even more broadly speaking, because they're perhaps not less in Europe, but internationally they're huge geological formations, potential storage sites in carbonates. So what about carbonates?
Yeah, no, we did not consider those for our geochemical reaction rates. I think if you look at the underground gas storage portfolio in Europe, not want to stare blindly at that, but the amount of carbonate reservoirs in that portfolio is extremely limited. I think it's maybe 1%. So yeah, also from that perspective, and there are some other complications, I would say, but we decided to go for sandstone reservoirs and look more at specific reactions like this pyrite to pyranite. Yeah.
And speaking of chemical reactions, Kishan asks, did you do any mechanical integrity tests after the geochemical tests at Edinburgh University to see how the mechanical properties of the rock change after they're being exposed to hydrogen?
Yeah, thanks for that question, Kishan. Indeed, well, we did not. We are doing. so this is work in progress, indeed, and that is exactly what we're doing: exposing the rocks first to hydrogen, and then doing geomechanical testing on them. I have no results yet, unfortunately, but they will follow in the second half of the project. Sorry about that. Yeah.
No problem. And we can just always invite you back once all the reports are
absolutely
finished. And we mentioned Arno, and Arno also has a question. Says, hello Remco, thank you for the interesting presentation so far. Did you do any work on upscaling the reactor scale microbial activities to the reservoir scale?
I guess upscaling I would say by modeling or something then, or
yeah.
I guess so, right? I mean, I'm not sure actually. I mean, this is really Diana Wageningen University work. As far as I know, they are not working on that at the moment. Of course, they do have samples from different sites that they are doing the experiments on. indeed, then linking it back via, for instance, geochemical modeling to field scale is not in scope, I believe. No, not in their work, right? So in work package 6, we are looking into the simulation work package. We are looking at more reservoir modeling, field scale modeling, and developing tooling for that.
Thank you. And last question. So on the microbial side, and Martin Wagner has asked, hello Remco, interesting results. Have you done microbial tests with core materials? They asked about carbonates, and we already discussed the carbonates. But have you done anything directly in the core? And also, did you work with 100% hydrogen?
Not with core material, no. We use these incubations. So basically taking sample material from the sites and doing experiments on those. So far at I believe at relatively low pressures of hydrogen, 1.7 bar. Also work on the way at higher pressures. And then carbonate, no, not on the core, no, not on core itself, no.
Okay.
With 100%, the experiments are with 100% hydrogen. That yes.
Thank you. And staying on to the core experiments, back to a question from Jan, and I had a related question. So, are there any differences for the relative permeabilities between natural gas and hydrogen? You mentioned the core flood experiments, the RELPER measurements at Edinburgh University. And the other question I had is, do you see any hysteresis in the relative permeability curves if you do cyclic imbibition drainage experiments?
Yeah, I have to refer to that question to Edinburgh. I'm afraid, okay. Because I don't know the intimate details there.
And I study the papers of them as well and reports.
Yeah, of course, you have papers out there. So indeed, yeah.
I could answer that from top of my mind by reading those literature, but I rather they just directly access those references. So
indeed, yeah.
And then I take one last question again from Kishan, and that's more, you've alluded to this in your talk already, but maybe there's a comment that you can already have. Well, you said the geobiochemical effects on the well infrastructure. This is something you're working on as you speak, but perhaps you could comment if there's any evidence that this is going to be really important for hydrogen storage sites. Is there any field evidence so far? Any other laboratory evidence that this is really needed to study?
Well, if the HyUSPRe project itself, the work is still ongoing. But of course, there's a project in Austria by RAK that really does pilots mixes of hydrogen and natural gas injected into a reservoir, and also soon pure hydrogen injection into a reservoir. And there, some of these risks are still relevant to study for them. So they did study them for the underground sun storage and sun conversion projects, right? And it's clear that from those results, further work is required. Okay. So they are definitely relevant. Yes. Yeah. Maybe specifically on microbial induced corrosion, but because that's more a link to the well. I think it's clear that MIC, as the acronym is can be a concern. We know this from the surface, and shallow depth, right? So and I guess also for larger depth, microbial induced corrosion, can affect the well materials, and particularly steels. So, yeah.
Okay. Thank you very much again, Remco, for a really nice talk. Thank you to our audience for the great questions. Sai Jangda just mentions in the chat and says the HyUSPRe workshop clashes with Interpor in May, so maybe there's the ever so small chance to change dates, either of Interpor or of the workshop.
Interpor people are on call and attending an online conference, we know where they are.
I think that's the Histories workshop, actually. I think that's the final conference of Arnaud.
Oh, right. Yes. Arnaud.
Yeah. That's fine. That's unfortunate.
So, well, thank you very much again, Remco. Hardy, over to you.
Yes, thank you. And just saying that since Arnaud is here, it says yes, they did different perspective as you did, and they did not look into gas sites that would be kind of repurposed for it, and this, which is great. I mean, this is the whole studies together collectively would give a lot of confidence about
exactly
the solution, and I'm really delighted that you got in different perspective to it. So thanks a lot, Remco. You know, we are very much hydrogenic. We are very much into hydrogen. I hope that many more studies, many more projects will come in future as well. So thanks a lot again for this extremely interesting and informative talk. I'd like to take the chance to introduce our next speaker. We will have our next speaker, since it's clashing with May vacations, etc. We are going to have the next talk webinar on 1st of June with my very close colleague, Femke Vossepoel, Professor Femke Vossepoel from TU Delft. She will speak about data assimilation, uncertainty assessments, and inverse modeling. So until 1st of June and much later, stay happy, healthy, and also tuned into our channel for another geoenergetic and geoscientific talk. Thanks a lot, Remco. It was a pleasant evening having you.
It was my pleasure. Thanks a lot for your attention, and talk soon.
Yes,
Thank
yes.
you.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.